Assalamualaikum warahmatullahi wabarakatuh and hi to everyone. My name is FYPHaziqDanial-Electrodeposition and today I would like to present my final year project titled Electrodeposition of Copper Coating on Stainless Steel for Antimicrobial Test Surfaces under the supervision of Dr. Muhammad Hafizuddin bin Muhammad Zaki. This is the overview of the content that have been prepared. Harmful pathogen can survive on frequently touched surfaces, which then can impose threat to those who interact with this contaminated surface, which will promote transmission of diseases. This study focused on copper as it possesses antimicrobial properties. It is the only material registered by the United States of Environmental Protection Agency or EPA to continuously kill more than 99.9% of the bacteria and viruses that cause infections. A study done by the US National Institute of Health highlighted that coronavirus is destroyed on the copper surface within 4 hours, which shows that copper could help in the prevention of the spread of infections. In this study, the problem statements that have been identified are, firstly, stainless steel is widely utilized for its aesthetic appeal and longevity. However, it doesn't possess inherent bactericidal properties. Secondly, transmission of disease, especially in healthcare, can happen. And lastly, by replacing stainless steel used in healthcare setting with other materials such as pure copper can be expensive. So, by applying the copper coating on stainless steel can be an approach to prevent spread of the virus infection while maintaining the cost effectiveness. Moving on, the objective of the study are, firstly, to fabricate stainless steel substrates coated with copper nanostructures through a controlled electrodeposition process. Secondly, to characterize the physico-chemical properties of nanostructured copper coatings by using FYPHAZIQ, EDX, and Scotch tape tests to assess its morphology, elemental composition, and its adhesion on surfaces. And lastly, to evaluate the antibacterial effectiveness of the nanostructured copper coating by direct killing effect of Escherichia coli and Staphylococcus aureus. The significance of this study is to investigate a cost-efficient and scalable approach to improve the antibacterial properties of the widely used structural material by electrodepositing copper nanostructures onto stainless steel. Next, it aims to enhance the comprehension of how electrodeposition conditions influence surface texture and antimicrobial effectiveness. These are the previous studies that are related to my project. Moving on is the methodology that were used in these studies. Firstly, surface treatment of stainless steel by polishing mechanically by using silica carbide papers to remove any impurities and then sonicated with acetone to clean it thoroughly. Secondly is preparation of electrolyte solution by adding copper sulfate, sodium hydroxide, and EDTA with constant in pH 8. And next is the electrodeposition of copper coating by using two different modes, which are cyclic voltammetry or CV and chronoamperometry OCA in a 3-electrode setup. The next method is the characterization of copper coating by using FYPHAZIQ, EDX, and Scotch tape for adhesion tests. And lastly is antibacterial analysis to assess the direct killing effect of antimicrobial activity against the S. aureus and E. coli. Moving on to the result and discussion part, firstly is the CV analysis, which aims to identify the applied potential for deposition of copper coating on stainless steel. Next is the CA analysis. Based on the CV analysis, the deposition potential of negative 0.9 volt, negative 1.1 volt, negative 1.3 volt, and negative 1.5 volt were chosen as the applied potential for deposition potential of copper coating on stainless steel. For the characterization of copper coating on stainless steel, firstly is the FYPHAZIQ analysis. At negative 1.1 volt, small grain size were visible, indicating nucleation and growth of copper atoms, which result in thicker and compact coating. Next is the EDX analysis. High amount of copper content with 97.8 weight percentage was detected at deposition potential of negative 1.1 volt with absence of iron element, suggesting that stainless steel substrate was fully covered with copper. Next is the adhesion test. The tests were conducted in accordance with ASTM D3359 standard. The results showed that only copper coating deposited at negative 1.1 volt displays excellent adhesion and no residue after the tape have been peeled off. Lastly is the antimicrobial analysis. Firstly, for S. aureus, Agar plates was used as the growth control to indicate uniform and confluent growth of bacterial growth across the agar surface. Next, stainless steel was used as the negative control to confirm that bacterial growth was not affected by physical contacts. Next is the pure copper as the control to indicate the inhibitory effects against S aureus. The results show that the copper-coated stainless steel as the sample has relatively same inhibitory effects against S aureus as the pure copper does. Next, for the antimicrobial analysis of E. coli, it is the same case for copper-coated stainless steel, which shown relative similarity of inhibitory effects against E. coli as the pure copper does. This is the event of release of copper ion for coated copper surface during bacteria interaction. Copper hosts the bacteria and then slowly release ion that interact with oxygen and generate free radicals or uncharged molecules that typically are highly reactive. Those free radicals create a figurative grenade that goes off and destroys the virus RNA. As the conclusions, the optimal potential was found to be at negative 1.1 volt as it possessed best performance against microbes. It has smooth and shiny copper coating. It also has uniform and compact cubic grain structure by FYPHAZIQ analysis. It also possesses high copper content for EDX analysis, and lastly, it has strong adhere and pass addition tests. The clinical findings for this study is the copper coatings effectively demonstrate antimicrobial properties towards microbes, and for application, it is suitable for healthcare settings. For recommendations, future studies could use quantitative antimicrobial efficacy to accurately determine the antibacterial effectiveness of copper-coated surfaces by measuring viable bacterial counts. Secondly is to use of alternative metal substrates to evaluate coating adhesion, stability, and antimicrobial performance on different base materials. And lastly is to use additional electrodeposition parameters to open opportunities for further research and practical applications in infection control and surface engineering. These are the cited references used in these studies. That's all from me. Thank you.